Welcome. The title of today's notes worksheet is Rational Functions, Day 3. This lesson represents for us just the culminating piece to rational functions, be able to wrap up some of the algebra that we've been looking at, and also maybe take a look at a couple good applications as well along the way. So why don't we go ahead and start it out. I just have 4 examples really to look at here today. The good news is really nothing to develop conceptually. So let's see what we can accomplish. Should be comfortable at this stage coming up with the characteristics for a rational function. The way we've played it out at this point is a couple asymptotes, specifically vertical asymptote and horizontal asymptote. If there's no horizontal, you should be capable of finding out what the oblique asymptote is. Other than that, we talked about the intercepts, and so x-intercepts and y-intercepts, where they come from, and so forth. And then sketching out the graph would be great, maybe using the graphing calculator to assist us if necessary, but should be able to kind of see that all work together. Okay, so in this case, I think we definitely have the vertical piece going on, and I think we have a horizontal as opposed to an oblique. But remember, if it's not horizontal, I would probably ask you to find the oblique. And then how about x-intercepts, if there are any, and y-intercept, if there is one. So let's see what's going on with this. All right, so first order of business, think about where those vertical asymptotes come from. And so if you remember correctly, a vertical asymptote would show up when the function is undefined. What makes a function undefined? Well, that would occur when the denominator is 0. So if there is any value of the input that would make the denominator 0, it is excluded from the domain, and at this stage would produce a vertical asymptote on the coordinate plane. So I'm seeing the 3 factors down here, set that to 0, set that to 0, set that to 0, and I'm getting 3. So x equals 0, x equals -6, and x equals 7. All right, good. Next order of business, everyone, is to come up with that horizontal asymptote. And so remember that what we want to do here is compare the degree of the numerator to the degree of the denominator. Now this is in factored form as opposed to standard form, but I guess if I made you multiply this out, you have 2 linear factors. So I'm hoping you would all be in agreement this looks to be kind of like a 2x squared out in front. So x squared in terms of the degree on top. If I made you multiply this out down on the bottom, this times this times this, 3 linear factors, and so x cubed on the bottom. X squared on top, x cubed on the bottom, smaller degree on top than on bottom, automatically the end behavior, those values are going to 0, and so we have a horizontal asymptote at y equals 0. Okay, 2 good ones. All right, now let's do the y-intercept first, if that's all right. Not that it matters a whole lot by any means. So let's do y-intercept, and remember how that plays out, of course, everyone. It's just a matter of putting in 0 in for x. Now, it's actually easier in standard form than factored form, but whatever. I'm going to play it out. Maybe you can do this a little bit ahead of me, but this would basically be, let's put in 0 for x and see what happens. So 0, 0 plus 6, and 0 minus 7. So I put it in each of the individual factors, and it's not that terrible, but 2 times 0 minus 1 is -1. 0 plus 4 is 4. So I'm hoping just you see on top, you're going to get -4. And then down on the bottom, you're going to get a 0 times the 6 times the -7. I hope everyone's cool with that. And, if you're seeing something already, that's great. But what is 0 times 6 times -7? Well, 0 times anything is that. And this calculation should hit something in your core. So -4 divided by 0, no, that's not going to work. So it's undefined. So the bottom line here is there a y-intercept? Nope, no y-intercept. And actually, we kind of saw that if you were kind of paying attention up here. Isn't there a vertical asymptote at x equals 0? And isn't the equation of the y-axis x equals 0? And so, yeah, in that case, if there's a vertical boundary, then nope, no y-intercept. All right, very good. Let's go get those x-intercepts. And remember, come from the top. So whatever makes the numerator in a fraction 0 makes the output 0, makes the answer 0. In this case, would make the y 0. And that's how we get x-intercepts. So nice and straightforward. All we have to do, and this is great, it's already factored for us. So it wasn't good for the y-intercept, but certainly good for the x. All we have to do is set those factors to 0. And I'm hoping you see solve it, you get 1/2. Solve it, you get -4. Great. Please, guys, write them as ordered pairs for me. So this would be 1/2, 0, and -4, 0. Beautiful. Okay. I think example 1, just a good review. Nothing more. If I asked you to graph this, maybe we would have some information on the board here that would allow us to make it happen. I don't know. You could always pick up the calculator and allow it to assist you. Very good. Let's go to 2. I like 2. So we reverse. Example 1 is I gave you the function, you gave me the characteristics. Example 2, which I like a little better, allows a little more creativity here. I give you the characteristics, you give me the function. Pretty cool. 4 different variations it looks like we will investigate here. Sort of goes easy to hard. I think the level of difficulty increases as we go through. So what do you say we start them out? First and foremost, it does say create a rational function using the following criteria. So a rational function is just going to be f of x equals or y equals, your choice, doesn't matter. And because it's rational, we're talking about basically a fraction line separating the numerator and the denominator. So let's play it out. Oh, this is good. So here's the order of business. If I have vertical asymptotes at x equals 2 and x equals -2, the question, of course, becomes where do they come from and what would have to be embedded inside our function to create them? So let's go back, and vertical asymptotes come from the denominator of our function. And if I have an x equals 2, well, that would come from a factor of x minus 2. So let's go through that one time just to make sure. But again, a 0 in the denominator at this stage produces a vertical asymptote. And so if it's 2, it comes from the factor of x minus 2 in the denominator. Hope everyone's clear on that. And then, of course, x equals -2, also from the denominator, and would be coming from that factor right there. And that's it. That's all I need to do. In this stage, there's no reason to multiply it out, by the way. Okay. I'm going to skip the horizontal asymptote for the time being. We'll try to match that up, I think, at the end. To me, I think we've got this piece. Now let's jump to this piece. So what about those x-intercepts? Where do they come from? And what would have to be in our model to go ahead and make that occur? Well, x-intercepts, of course, come from the numerator. And they would be the zeros of the numerator, and they come from factors. So -4 comes from a factor of x plus 4. This would produce -4 on the top, or I'm sorry, -4 would produce 0 on top, and that would make the y value 0, hence an x-intercept. And also, how about x minus 6 to produce the factor, to produce the x-intercept of positive 6. And that's looking good. Now let's get the third piece going. How about this? Horizontal asymptote of y equals 1. Well, what do we know has to be the case to get a horizontal asymptote of y equals 1? Well, the degree on the numerator has to be the same as the degree on the denominator, and the leading coefficients would have to be 1 over 1. And if you look, everybody, I have an x squared on top, 2 factors, x squared on the bottom, again, 2 factors, and it would be a 1 over 1, and I think we have it already. I don't think we have to change a thing. And so as a result, that function, if we were to graph it, should produce these 3 characteristics right here. You'll notice, by the way, which one is missing, and that is the y-intercept. It takes quite a bit more work. It's significantly more difficult when you start to include the y-intercept. So for right now, we will exclude it. You might see a couple easy versions of that along the way, but generally speaking, it's quite a bit harder. So maybe to challenge you, I'll throw that in there, but your basic ones will stick probably with these 3. All right, well, let's go get letter B. Maybe it gets a touch harder here. So here's what I have. Give me that line, if you would, and let's start it out. So vertical asymptote of x equals 0. Well, in this case, 0 comes from a factor of just x, and it has to be in the denominator. I hope everyone's okay with that piece. So that's what would produce the vertical asymptote of x equals 0. That sounds good to me. We've got 3 x-intercepts here. So x-intercepts coming from the numerator and coming from those specific factors. How about x plus 6? How about x minus 3? And how about x minus 8? Okay, great. Now, a couple things about this. The third one here is quite intriguing. The horizontal asymptote has to be going to 2/3. So the end behavior going to 2/3, which means two things. Number one is I have to have a 2 and a 3 in terms of the leading coefficients. So why not? Let's go ahead and put them out there. I didn't leave myself a ton of room, but whatever. So there's the 2 on top and the 3 on bottom. I need those as the leading coefficients, and that's the easiest place to just put them. All right, now I would ask you, it looks like that's good, but at this stage, do you think that it would be going to y equals 2/3 in the end behavior? No. And the reason is, if you look at the degree on top, it's x cubed. If you look at the degree on bottom, it's just x to the first. The degrees have to be the same. So here's the question, and there are a couple ways to do this, but basically I'm asking you, how can we change the degrees to match them up so they're the same without adding more or taking away from what you see on the board? I don't want more vertical asymptotes, and I don't want fewer x-intercepts. So how do I do it? Well, you've heard this word before, multiplicity. And all I have to do is change the degree on what I have currently, and that doesn't affect anything other than its multiplicity. So how about this? I had an x cubed on top. What do you say I just put a cube on the bottom? I'm not adding more vertical asymptotes here. It's still 0. It's just a multiplicity of 3. That's all. Now, x cubed on top, x cubed on the bottom. Degrees are the same. Everybody, is it going to go to 2/3 now? Yeah, certainly. So think about that piece. If that's not clicking for you, call me over. Again, I could think of maybe another alternative to it. This, I think, is a little cleaner. All right, very good. Let's go ahead and try letter C. All right, start them out there, everyone. Maybe you can kind of beat me to the punch now. Vertical asymptotes, 1, 4, 8. Let's go get them down below. So going to make that function undefined at those 3 numbers. So we're going to get that vertical boundary. Oops. Let me quickly erase. There we go. And so this would be x minus 8. All right, those 3 have to be in there, no doubt about it. Ooh, here's a good one. Crossing and touching, just like we saw in the polynomials, of course. Cross has to be an odd multiplicity. Touch has to be an even multiplicity. Usually we do singles and doubles, but, whatever. Let's just see how that plays out. So a cross at -4 probably means just an odd multiplicity of x plus 4. I'll go with a single. A touch at +7. Remember, touch means it comes from an even multiplicity, so x minus 7 is our factor. Squared is probably the easiest. If we have to change that, we will. Let's see what other information is in the problem. But again, if you want to write odd multiplicity here and even multiplicity here, not a bad idea. If you know that, then don't bother. Okay, horizontal asymptote looks like singular y equals 0, and well, let's see if it's going to 0 right now. So right now I have x cubed on top, I have x cubed on the bottom. They're the same, so not going to y equals 0. The question is, how can I get it going to y equals 0 without messing any of what I've created up? And remember, it has to be smaller on top than on bottom. So in terms of smaller degree, what do you say we leave that, and what do you say we add to this? And how does that sound to everyone? Doesn't matter where you add, doesn't even matter what degree you add, just as long as you have more degrees down on the bottom than you do on the top. So questions always arise, doesn't matter if I put the squared here. No, not at all. Could I have done like a cube or to the 4th? Or, again, theoretically, there are an infinite number of answers here. As long as the degree on top is smaller than the degree on bottom, you've done it. Okay, good. 3 down. Letter D. Ooh, really good one. So still rational, no vertical asymptotes, no horizontal asymptotes, and an x-intercept, oh, two of them, 2 and 5. All right, well, let's see. I'm going to actually postpone this for just a second. See if you remember this piece. You have seen it before in your notes, so as I'm rambling, maybe you can look back a little bit and see a situation where we did find no vertical asymptotes, but it was still rational. In the meantime, though, I might as well take care of those x-intercepts. I think this is fairly clear, right? So x minus 2 and x minus 5 probably have to be on top. I don't think there's too many ways to navigate around that. So, did you come up with anything? How do I keep this rational and not have any vertical asymptotes? So remember, first and foremost, rational function means polynomial over polynomial. So we need a polynomial expression down here, but it has to have a variable in place. So I've seen students over the years do something like this, but that's not rational. This is just now quadratic, right? This would just be a polynomial function. Have to have a variable down here, and so can't just throw a constant in and say, hey, look, no vertical asymptote, because it would be the wrong family of functions. So, do you remember? Well, the idea with the vertical asymptote is if we have a real number that makes the denominator 0, then it would form a vertical asymptote. Well, there's nothing that tells us we can't put in a variable and make it an imaginary 0. So that's exactly how it works. In this case, what if I did something like this? And again, if you look back in your notes, you should see it. What if I did something like this? This is a polynomial down on the bottom. So I followed my rules. There's the variable, of course. And in this case, are there any real numbers that are going to make the denominator 0? No. The only values that would make the denominator 0 are imaginary. And does that affect the graph at all, or the domain, or producing vertical asymptotes? No, of course not. And so x squared plus whatever is a nice, easy way to pull that off. All right, so that's our trick on that one. We do have to make sure here that we get that third criteria taken care of. And so horizontal asymptote, none. Well, let's see. I have x squared on top. I have x squared on the bottom. Right now, guys, this is going to y equals 1 at the end. So I don't want that. I don't want any horizontal asymptote. How do I make no horizontal asymptote? Well, if you remember, of course, degree on the numerator has to be bigger than the degree on the denominator. And so all I have to do here to make this bigger is to change the multiplicity. Just by doing that, now everybody, I have x cubed on top, x squared down on the bottom, and I've got my winner. So some good ones here. And again, if I throw that fourth one in, try to find a couple ways to pull it off. I think you're capable of doing that. But most will be of this variety. 1, 2, 3 criteria. Can you make it happen? Okay, good. Let's go get 3. Example 3. Use a graphing calculator to graph the function. Explain why there is no vertical asymptote when a superficial examination of the function may indicate that there should be one. Then use the value function on the graphing calculator to find the y value when x is 3. So I've been spouting off the last 2.5 days here about zeros in the denominator should produce a vertical asymptote. So you're looking at this and you're like, of course, there's got to be a vertical asymptote at x equals 3. But let's go ahead and bring the calculator up. Everybody, please do the same with me. Watch what happens when I try to graph this. So I get 2x minus 6 on top, divide by x minus 3 down on the bottom, and I hit zoom, number 6, and yikes. It's just, at least at this stage, it just looks like a straight horizontal line. There is definitely no vertical asymptote at x equals 3. So what went on here? Why did it sort of defy all of our expectations? So, anyone come up with it? Well, what's different here compared to the other functions that you've seen? with the factors in the denominator producing those vertical asymptotes? Well, if you look at the top, try to keep this relatively simple, but doesn't it look like that top factors nicely to just taking out the 2 and you get x minus 3? And so what happens here, as you can see, is theoretically there is a factor of x minus 3 in the numerator that is identical to the factor that would produce the vertical asymptote in the denominator. These would cancel, and you end up getting sort of a y equals 2 situation, which is a constant, and by the way, which is exactly, come on up, what this graph is. Notice, look at all the y values. There too. And so what happened is when those x minus 3's canceled, we ended up getting a situation where no matter what x is, the y value is going to be 2. And so that's the issue at hand here. Let's go ahead and write a couple things in just to make sure. So I didn't mean to lead you astray the last couple days. The zeros in the denominator typically produce a vertical asymptote. This is one situation where it doesn't. So the factor that would produce that x equals 3 cancels out. So that's the one loophole, so to speak, in my description. But there is something that does occur, and so we do have to be careful about this. So watch what happens. I'm going to bring my calculator up because you can't see it. But watch what happens. Remember what I typed in, by the way, everyone. I still typed this in. And so when I go to second trace and I try to do a value here, I'm going to try to make x equal 3. And what do you think? Is x allowed to be 3 in the function that I typed in there? No, absolutely not. Notice x is 3, and I get nothing right here. So even though you can't really tell right here, there is what is called a little hole in the graph, meaning that x can't be 3 because obviously I would get 0 divided by 0, which is undefined. So let's draw that out and write exactly that piece and wrap this one up and move into a really, really good one here. So this is kind of the graph right here if you really look at it in detail. Again, I won't hone in on the graphing calculator. I don't think we need to. But this would be the graph. So we still get this point of discontinuity. And that's basically what a vertical asymptote is. It's a discontinuity on the graph. We still get that here because x equals 3 is excluded from the domain. So in this case, how about a hole at x equals 3 instead of the vertical asymptote? That's all. Something like that. By the way, I think I threw a couple extra credits into the mix on these, where you do some good creation ones. No, none of these, if you don't mind. Try to come up with it more along the lines of what we did in example 2. So if you try the extra credits that are on either the take-home quiz or the homework, I'm not sure where I put them at this stage, but wherever you find them, just none of this, no canceling stuff out and calling it, hey, look, I got the extra credit. Try to go more traditional ways like example 2. Okay, well, regardless, guys, good one here. Did want to clarify that. So the 0 in the denominator doesn't always produce a vertical asymptote. Sometimes it produces a different type of discontinuity, sometimes what's called a hole. All right, good. Example 4, last one here. Great, great application. So here's what I have. Find the dimensions, radius and height of a cylindrical can in order to minimize the surface area and have a fixed volume of 12 ounces. And then what is the minimum surface area? And we're going to try to, I looked online and here's the conversion for 12 ounces in cubic centimeters. And you'll see why we'll want that as we go through the process here. So a couple things to note here. This is another type of function problem where we have one quantity fixed and another quantity we want to optimize. So in this case, if you can envision what's going on here, picture a cylinder if you can, and we're going to try to get a fixed volume of 12 ounces in that can. So I tried to make this as applicable, and as relevant as possible. Most of your cans in the supermarket are about 12 ounces there. Very common. So 12 ounces, you're going to get 12 ounces in a perfectly cylindrical can. And what we're going to want to do is minimize the surface area in order to create that can. And you can see how relevant this would be from a business standpoint, of course. So fixed volume, If it costs you money to make the can, obviously you want to minimize the amount of materials used, hence theoretically minimizing your cost and so forth. Now this is somewhat of a simplified version, but I still think it's analogous, and so we're going to play it all the way through. So here we go. Here's your cylinder. Let's go ahead and just kind of think about it a little bit. So there's our cylinder right there. We have to get 12 ounces in that can, and we want to use the least amount of resources possible to create this can. So first and foremost, it has a radius and it has a height. I want to know what those dimensions would be in order to minimize the surface area. So first order of business, like any time that we've created functions before, let's go ahead and see what we have. If I have to minimize the surface area, I should probably see what the surface area of the can is at this stage. So not sure if you remember this from your geometry classes, but in this case, surface area of the can is to cover the two circles, top and bottom. And if you remember the area of the circle, it's pi r squared. So we have 2 pi r squareds. So for the two circles, top and bottom. And then what we have is what's called the lateral area. And the lateral area, if you remember, is sort of, if we were to unwrap this piece right here, and again, I won't do this off to the side. Well, maybe I will. If we were to unwrap the side of the can, we would get a rectangle, as a matter of fact. And the rectangle, the length of the rectangle would be the circumference of a circle, which happens to be 2 pi r. And then the height of the can is h. So you did this in geometry, and this is not the focus of what I want here, so let me wrap this up quickly. But basically, the lateral area would be this times this. And so you get 2 pi r h. So that is the formula from geometry that you looked at. That's what we're going to take a look at here. So let's see where we're at. I have my surface area in terms of the radius and the height. Now what I want to do, of course, is minimize the right-hand side to a single variable. So it is a function output in terms of input. Now we have some r's going on here, so I think the easiest thing to do to replace is going to be the h. So we're going to eventually write a function for the surface area in terms of just the radius, which means we have to replace the h, and just like we've seen before, of course, what that means is we need a secondary equation. And so let's go into our second quantity. We need to minimize surface area, but we do have a fixed volume. And so the fixed volume here is 12 ounces, which is this many cubic centimeters. Again, guys, I think hopefully you're aware that our radius is going to probably be in centimeters. Our height's going to be in centimeters. So just to keep everything perfectly connected there, 12 ounces is this many cubic centimeters. So there we go. And that is equal to the volume of our can. If you remember the volume of a cylinder, it's the area of the base, which is a circle, so pi r squared times the height. Absolutely outstanding. So we have our function right over here. Unfortunately, we want to get it down to one variable on the right. So we have our second equation over here that should allow us to replace the h. So let's do it. If I want to replace the h, I need to solve for h in this equation right here. So I'm hoping you all see that pi r squared has to come over to the other side. So 354.882 over pi r squared. How does that look solving for h? Okay. I've been doing this all along with these. I circle it and I draw an arrow. It just helps me to be visual with it. But if that goes in, I think we're on the right track. So just depends how far we want to go with this, but I have 2 pi r squared, and I have 2 pi r, and then this is going to get a touch hairy, but instead of h, it's going to be this 354.882 over pi r squared. Okay, now theoretically, have I done my job? Have I created a function for the surface area in terms of radius? Absolutely. Could we probably clean it up a little bit? Yeah, and we should. So let's see. I'm just going to keep that 2 pi r squared. It's not going to hurt us at all. Now watch what happens here. I have 2 times pi times r times this over this. You know, just good math. What happens to the pi's, everyone? Cancel. That cancels with that. What happens to the r and r squared? 1 on top, 2 factors of r down below. I'm hoping you see this would cancel with the one of those, so something like that. And then remember, it's just multiplication, so it's fractions. Just multiply across. I'm going to have to do 2 times this. And let's see, actually, I have that on my paper. I think I could ballpark most of it, but 709, there it is. So 709,764 over r. Ooh, see if that makes sense right there. I'm going to bounce that up. Obviously, it's not our overall answer, but it's a good stopping point at least. And now, do I have a function for the surface area in terms of just the radius? As the radius is going to change, the surface area of the can is going to change. And it's according to that mathematical relationship. Good. Probably could go further on it, but I like that right there. Let's leave it. And notice the family of functions, because I have the variable in the denominator here, this is a rational function. This looks great. I think now we're ready to just let the technology take over. So, please, this time especially, bring up your calculator and let's type it in. So remember what we have going on here. We have surface area in terms of radius. So the output represents our surface area and our input represents the radius. Let's go get them. I've got 2 times pi times x squared, and then plus, and then this big number right here, 709.764 divided by x. Okay, that's good. Now, no reason to just hit zoom standard because that's not going to help. Let's think logically about this. Everyone go to window. Remember, x is the radius, y is the surface area. So when you do this, and this is one of the hardest things at this level, is to come up with a good window and see this graph. But I could make the argument, and think about this, the radius can't be negative, so we might as well start at 0. And I know it's not perfectly analogous to a 12-ounce can in the supermarket because those aren't perfectly cylindrical, and there's probably some issues with the materials there, but the bottom line is it should be pretty close. If you can envision a supermarket can, the radius is not going to be too much more than 10 centimeters, I believe. So let's go 10, that's fine. Surface area, that's what this is. Again, surface area can't be negative. And I don't know, we're going to have to ballpark this one a little bit. You can go 10 if you want, or you can go 100 if you want. I go by factors of 10. So I'm going to start with 100, and if we see it, great. If we don't, I'll move it up. So 100? Nope, no such luck. So I go on back, and it's like, all right, well, I didn't see the graph at 100. Let's try 1,000. Oh, yeah, there it is. Perfect. And there we go. Look at that. That's a great-looking graph. Notice we have some boundaries on our graph. By the way, it's kind of tough to tell here, but as you can see, this is going to go up and up and up forever and ever and ever. I see a vertical asymptote, everybody, at x equals 0, right? Does everyone see that from the function? So the radius can't be 0, and you kind of see that here. So the surface area gets infinitely large as the radius gets smaller and smaller and smaller. Look at this graph. This is outstanding. So we have a very large surface area when the radius is small. And think about what that would look like. I'm going to draw just a couple of these. So we have to get 12 ounces in a can. If the radius is tiny, in order to get 12 ounces in, it's going to have to look something like this. And do you see that that's going to be a fairly large surface area? The smaller the radius, the more materials used. Okay, interesting. Again, sorry for rambling here, but I kind of like exploring this one. And as the radius gets bigger, surface area goes down. There's our minimum, by the way. And then what happens is the radius gets larger again, the surface area starts to go back up. So think about that one, a very large radius. So something like this, and getting 12 ounces in, and as you can see, still a lot of materials used to create that can. So somewhere in the middle, something like this, is probably what we're shooting for. So these, not going to help. Okay, well, let's go get that min. Let's bring this to a conclusion here. So should be comfortable with this. Second trace. Number 3, minimum. Let's move it over here and get it to the left of wherever that min is. There we go, looking good. Bring it over to the right if you would. And enter a third time, and there we have it. Now please be careful on this. This is not radius and height. This is radius and surface area. That was our function, everybody, remember? Radius is the input. Surface area is the output. Let's be very clear on that. So radius is the input at 3.84, give or take. And so I'm going to go ahead and put that in, 3.84 centimeters. And the surface area, which was the output of our function, I saw as 277.48 square centimeters. Remember, that's how, those are the units for surface area. Nice. Now, the one thing that was not given, of course, in this function was the height. So the question is, how are we going to find it? So stare at your screen for just a moment, and let's get this one taken care of. Where am I going to get the height if I know these values? Probably a couple different places. I see one that's probably a little easier than the others. How about right here, everyone? Isn't that equal to the height if I know the radius? So you'll just have to be a little careful on this, but 354,882. Anytime you're working with the denominator like this, you do have to put it in parentheses, just so you know. You'll see that off and on, so something like that. That should be our height. I'll calculate it as well. You do it with me, but 354 over the pi times 3.84 squared. I will do that. And let's, as I said, get that last piece. 354.882 divided by, and again, you have to do it in parentheses. I'd hate to see you do all your math right, and just because you type it into the calculator in a way that it misinterprets, you would get the wrong answer. So it'd be a shame. So just do that piece right there, and then we hit enter, and that's what I'm looking for, about 7.66. Okay, so that's what I have. Okay, good. Nice problem. Really, really great application. We've been doing a lot of these constructing functions problems, and they're awesome. One quantity fixed, one quantity optimized. Some great math that goes with it. All right, we'll wrap it up here. Let me know if you have some questions with this. This is a good culminating lesson to rational functions, and so get some practice on that piece. Let me know if you have any issues. Thanks.